Okay, let's jump right into this explainer. Today, we're putting on our systems engineer hats and looking straight under the hood of AI to see how true intelligence is really built. We are well past the era of simple prompt and response chatbots, right? We're living in the age of multi-agent systems now. And the real magic? It doesn't happen in isolated algorithms. It happens in the intricate web of interactions between them. So get ready, because we're going to look at the literal architecture that makes all of this possible. Now, I want to start by completely reframing how we view AI. It is so tempting to think of artificial intelligence as the single massive brain in a jar, just calculating answers all by itself. But for modern systems, that's fundamentally incorrect. An advanced AI is actually a network of distinct, highly specialized nodes, and its power relies entirely on how effectively those nodes talk to each other. I mean, you can have the smartest individual agents in the world, but if they can't communicate clearly, the whole system breaks down. Literally, at an enterprise scale, intelligence is communication. All right, here's our architectural blueprint for today's explainer. We'll cover the intelligence of communication, structuring the message payload, core communication patterns, a real-world trading system example, and finally, engineering reliable AI systems. So let's dive straight into Section 1, the intelligence of communication, looking closely at neurons and network nodes. What actually happens when agents start firing messages across a complex network? Well, at its core, agent communication is defined as structured message passing between agents to coordinate tasks, share data, and produce correct results. Think of this vividly, like neurons firing in a human brain. Your brain isn't just one static block, right? It's billions of neurons sending rapid-fire chemical and electrical signals to coordinate everything you do. In an AI system, these distinct agents are the network nodes, and the structured messages they pass are the vital signals aligning them toward a single goal. To bring that abstract neuron concept down to earth, imagine a multi-agent system as a corporate Slack team. Human-like coordination relies entirely on clear roles and targeted messages. And honestly, AI is no different. You've got the planner agent acting as the manager, assigning tasks. The retriever is your tireless researcher sharing data. The tool agent, that's the engineer running the numbers. The reasoning agent acts as the analyst, explaining what it all means. And the coordinator is your team lead, aligning the whole thing. If the researcher on your team drops the ball or sends a garbled message, the project stalls. AI agents operate under that exact same constraint. Which leads us perfectly into Section 2, structuring the message payload to prevent system errors. As a systems engineer, you have to look at this JSON payload right here like a cleanly manufactured part on an assembly line. When agents talk, they don't use casual chat, they use highly structured data objects. Notice these strict keys: identifying the specific agent, defining the exact task, housing the output data, and crucially, the reporting the status, which in this case is success. Every single micro-interaction in our AI Slack team relies on this payload being perfectly formatted. If you strictly define the task and status from step 1, you prevent a total system collapse later on. Because what happens when we don't have that structure? Without it, multi-agent systems fall victim to these incredibly common fatal errors. An unstructured message means the receiving agent literally cannot parse the instruction. It's just junk to them. A missing field, like forgetting the status tag, leaves the coordinator agent hanging infinitely, waiting for a success or failure state that's never coming. And then there's overcommunication, just pure noise. If an agent sends a massive text dump without validating what's actually needed, basically the AI equivalent of an overly long meeting that could have been an email, it totally overwhelms the reasoning agents and breaks the pipeline. Structure is absolute survival. Let's look at how we route those messages in Section 3, Core Communication Patterns, the architectural blueprints. These 4 patterns are specific engineering blueprints used to solve distinct architectural problems. First up is sequential. Think of it as a digital assembly line where agent A finishes its job and hands it straight to B, and so on. Then we have parallel processing, which is fantastic for speed. Imagine retriever A pulling financial data while retriever B pulls news articles at the exact same time, and then their findings merge. Third is broadcast, where a central coordinator shouts an instruction out to many agents at once. And finally, the most advanced pattern, the feedback loop, which creates these incredible self-correcting cycles. The feedback loop is truly the holy grail of machine autonomy. Zooming in, we can see exactly how an agent physically self-corrects using structured communication, step by step. First, the agent attempts an action, let's say writing a block of Python code. Second, it sends that code to a tool agent to run it and receives a structured result back, maybe an error message. Third, a reasoning agent ingests that error, improves the approach, and step 4, retries the task. This loop continues until the system receives that beautiful status success payload we looked at earlier. It's a fully closed-loop system of iterative intelligence. Now, let's put this into practice in Section 4, Example, the trading system, a live stress test. Picture this: high stakes, real-world scenario. Notice the rapid-fire forward momentum here. At exactly 0 milliseconds, our retriever agent triggers to fetch live market data. By the 15-millisecond mark, the message payload is securely handed to the tool agent, which instantly processes complex technical indicators. And by just 40 milliseconds, the reasoning agent has digested the entire package to make a critical financial decision. I mean, this timeline shows how impossibly fast these message exchanges fire across the network. If there is even one missing JSON bracket, this entire 40-millisecond pipeline halts, and a lucrative trade is completely missed. So, in this specific stress test, the retriever acts first, grabbing a precise price point off the wire, an asset trading at $22,450. It passes that structured number to the tool agent. The tool agent runs its math and flags a downward trend, specifically noting a relative strength index, an RSI, of 28. For those who don't know, that is a highly bearish signal. Finally, both of these perfectly structured data points hit the reasoning agent, which evaluates the context and makes the final call. Wait, not a strong buy. Simply through clear, sequential message passing, the multi-agent system just saved a portfolio from a terrible trade. Finally, let's look at how to scale this in Section 5, Engineering Reliable AI Systems, Beyond the Basics. Look, building a toy system is easy, but building an enterprise architecture, that requires advanced networking capabilities. First is shared memory, ensuring all agents have a single source of truth by reading and writing to the exact same state database. Next is event-based triggers. Instead of an agent constantly bugging the system asking, "Are we there yet?" it simply waits dormant until a new data available message physically triggers it into action. That saves massive compute power. Then we implement streaming for continuous real-time data flow, absolutely essential for that trading system we just saw. And finally, secure communication. We have to rigorously validate every single message payload to prevent malicious prompt injections from hijacking our internal agent network. Because when we ignore these strict engineering protocols, we get exactly what you'd expect on the left: confusion between agents, compounding errors, and a completely broken flow. It's the equivalent of a Slack channel where everyone is just shouting over each other in different languages. But when we enforce structured payloads, clear patterns, and secure shared memory, we get the right side: clarity and accuracy. The agents act as a unified, frictionless machine. The crucial, overarching takeaway from our explainer today is simply this: a system is only as strong as its communication. Intelligence isn't just computational horsepower anymore. You can have the most expensive, state-of-the-art language models acting as your nodes, but if their signaling is weak, your system is weak. When agents speak clearly, utilizing rigid, validated structures, the entire network stabilizes. The nodes align, and the system graduates from being a simple, automated script to becoming genuinely, autonomously intelligent. I want to leave you with this final thought to chew on. We just looked at a trading system operating in 40 milliseconds with just a handful of agents. But imagine scaling this. What complex global problems, from global logistics and supply chains to medical research and climate modeling, could we solve when millions of specialized agents speak perfectly clearly to one another? It's an incredibly exciting frontier, and it relies entirely on the architecture of multi-agent communication. Thanks so much for joining me for this explainer, and keep your eyes on the network.